So now we are getting into the fourth module of high voltage engineering, high voltage engineering subject, and what you are going to learn is high voltage measurement. Okay. So module 4 is basically about what? It is mainly about high voltage measurement, right? Like in the first three modules, we were learning about generation of high voltage, like whether you want to make an AC or DC or an impulse waveform, which is high voltage. That is what you are learning till this time, like high voltage generation. Now we are going to discuss some of the techniques which are used in high voltage measurement for reliable measurement, right? So that is what we are going to look into. Okay. So let us discuss some of the features of this high voltage measurement equipment. Okay. Like first point is this one, but the location and layout of the equipment under test. Means what? You are going to test a bushing of you are going to measure voltage from the bushing of a transformer, or under some particular instant, like inside your lab, you are going to test one of the equipment. So that time your measurement equipment also should, like your whatever you are going to conduct measurement and whatever measurement equipment you have, both you should be able to incorporate together, and where it is placed. These all things matters when it comes to high voltage measurement, right? It is not like you have a voltmeter or a multimeter and you can go and measure at in between any node. It is not like that. There are conditions about measurement and accessibility of that place. Then second part is that if you take a moving coil machine, instrument, or normally other instruments also, normally we can linearly extrapolate, right? Like for 5 ampere, this is the point, and for 10 ampere, it will be in the same line. Like that, you can extrapolate the response of the instrument quite directly. But when it comes to high voltage measurement, you cannot do that. Okay, because you will see why. Why is that so? So linear extrapolation of a device reading beyond the range is not valid for high voltage meters. That is the next point. Second one is there are problems when it comes to the calibration for the full range and all. Okay, it is not easy. That is what it is. And another major point is that whenever you have a transmission line like this, and when I say a high voltage line, like it is at very high voltage, not even 220, let us say it is at a very high voltage line. Then what? When I say voltage is null, then you can say that it is charged. So because since it is charged and you have some voltage which is on the transmission line, due to that you can have electromagnetic interference nearby the adjacent electronic equipments or nearby other things. So this electromagnetic interference that plays a main part when it comes to high voltage measurement and all, and we have to take care that the electromagnetic interference is not affecting our measurement. Okay. So these are some of the features we will be expecting from a high voltage measurement equipment, that you should consider where it is going to be tested, and you should also should not take it granted that you are working on a linear scale. Okay, because that will not be the case, and calibration is a problem, and your electromagnetic interference needs to be avoided or minimized. So that these are the 4 points when it comes to the features of a high voltage measurement equipment. Okay. Now, what all things we are going to be learning? What all things we are going to learn when it comes to measurement? Okay. So, what all things we are going to learn when it comes to measurement? What are they? Like when it comes to measurement, we are thinking about voltage and current measurement. That is why I wrote like this: voltage as well as current. We are going to measure voltage and current, and in this module, you are going to learn these voltage and current measurements in particular. Like voltage measurement, there are 4 things. Like one is shear gap, another one is potential divider, and another one is peak voltmeter, and the fourth one is electrostatic voltmeter. We will see one after another, and shear gap is what we are going to take up for the first. And I think such an application you have already learned in your impulse generator. Like whenever the shear gap comes to, like you have to generate some voltage, you will adjust the shear gap such that at a particular potential it is going to break down, right? So that voltage you know. So we are going to apply that principle to measure voltage, that is about sphere gap. Potential divider is also something quite not true, like you have a series of resistors like this. Okay, this is a potential divider, you apply a voltage here, and here you get an output which is proportional to this output, so that when you have a higher voltage on one side, that can be measured like linearly proportional, in a linear way, in proportional to whatever voltage you applied here. So that kind of a simple principle is there in potential divider. Then we have got the peak voltmeter. It is also called as Church-Fortescue method. Church-Fortescue method. This peak voltmeter is called as Church-Fortescue method. You will learn more about that. Then you have electrostatic voltmeter. So it's like a generating voltmeter. Then you have current measurement using the Hall effect, optical devices, Rogowski coil, and shunt measurement or resistive measurement. These are things you are going to learn in detail in this module. Okay. So basically always, whether it comes to instrumentation or measurement, you have seen this already. Like when you want to measure current in analog ways, in an analog instrument, what you will have a magnetic coil or something. So and you will use the current, and its effect is what? The magnetization of the coil and the deflection of the needle, right? So similarly here also we are by measuring I or V means what? We are going to measure some effect of I or V and indirectly obtain the value of the voltage and current. Understood? So that is what we are going to do, similar to the case. So here when it comes to sphere gap, it is the breakdown that you are going to measure. So similarly, or breakdown how much distance is needed. From that we will get our high voltage measurement. So we will get the measure of the sum of the effect of current or voltage, and we will indirectly obtain the value of voltage and current. That is what is going to be done for the measurement. In whichever case we are going to learn, this is what I can say is one principle of measurement. Now, let us start with voltage measurement and see the summarization. Like sphere gap. Sphere gap, in which all cases we can use? We can use it for AC, DC as well as impulse measurement. Right? We can use the same sphere gap for AC, DC and impulse. It is quite simple only, like you have two sphere gap connected like this, and you can adjust the gap, and you will note down the gap at which you have breakdown, right? And we already know what is the breakdown of air for a particular distance. We have summarized it. If we have summarized it, from a lookup table we can find out the gap distance, the corresponding voltage to the gap distance. We will discuss it later. And voltage divider also, they also can be used for AC, DC and impulse measurement. But when it comes to peak voltmeter, we can use it only for what? AC, peak excess current. So peak voltmeter means that we will be using only for AC. Then you have got electrostatic voltmeter, and it is normally used for AC, and sometimes we use it for DC. But we never use it for impulse purpose. We will learn more why it is so and all when we discuss the principle of each of this thing. So again I am saying, our intention is to measure what voltage and current. Our intention is to understand methods in voltage and current measurement when it comes to high voltage levels, and we will see one after another. And firstly we are going to see voltage measurement, where we are going to learn the four types, which are the sphere gap, voltage divider, peak voltmeter and electrostatic voltmeter. These are the four types of measurement that we are going to learn. Now let us discuss about the first type of voltage measurement, which we are discussing with what? With the sphere gap. Okay. We are going to use a sphere gap for measurement. Sphere gap, what is meant by sphere gap? You already know, like we already discussed. So two identical spheres of metal and a gap between them. That is what we have. Two identical spheres. Like you have two spheres. Okay. One is here, another sphere is here. So, and between them you have a gap, and we call that distance as d. So this is a sphere gap kind of measurement. This is a sphere gap kind of measurement. And for making the spheres, we normally use aluminum, brass, bronze, such alloys. So basically, we use some good conducting material and conducting alloys. Conducting material and aluminum, brass, bronze alloys are the material which we use for spark gap. Okay. And mainly when I say spark gap, it is about breakdown also, and there will be carbonization and all. So which type of material you use also matters. So you have two sphere gaps, and in between you have a distance thing. And we all know that air is having some breakdown voltage value. Right? So at a particular distance, it will break down. So that is the known part. Right. So there are four types of arrangement One is what? Sphere, horizontal configuration. Means you have a sphere like this. So like this, horizontally if we place two spheres and we adjust the gap so that breakdown occurs, and what we adjust the gap, and so what will happen? We will get a distance d, and you will have a chart. You will have a chart where you have a distance d and corresponding breakdown voltage is already there for a particular diameter of sphere gap. That chart is already there, or a lookup table is already there. For a particular distance, what is the breakdown voltage? Means that is the voltage at which breakdown is happening, and that is the voltage which you have applied across. So by adjusting this T and by making the breakdown to happen, you are finding the voltage whichever is under measurement for you. So that is the way the sphere gap is used. And for arrangement as the sphere horizontal configuration, this one is used for medium voltages. The sphere to sphere horizontal configuration is used for what? That is used for medium configuration. And the sphere vertical configuration, this one is used for normally for what? Very high voltages. So that is the difference. If normally in a horizontal position we use it for medium voltage measurement, in the in a vertical position we will be using that same for a high voltage measurement. Then you have the other two types. It means what? Rod means what? You have one rod here and one rod here. This is the rod type of configuration. So that is again same thing. Here what breakdown will happen. The change will be only in the way your electric field is. And point plane means you have a plane like this, and what you have a pointed electrode like this. So the breakdown between them and the distance is used to find out the voltage level. So in this rod or point plane configuration, that is normally used for low voltages. Understood? So this rod or point plane configuration we use for low voltages. Sphere configuration we normally go for medium or higher voltages. Medium is what? In medium, our configuration of the spheres will be in a horizontal direction. The vertical configuration is used for higher voltage levels. So this is about the types, and I think you got a preliminary idea about sphere gap measurement. What is that? Let us be clear about that. Like you have two sphere gap. First sphere gap, I am going to connect it to the ground. Okay. First sphere gap I connected to the ground. Let me call it as the second sphere gap. And the first one is where we are going to apply our high voltage. Okay. These both will be of the same diameter. First what we will do is that we will keep the distance d as very high. Okay. So that now no breakdown is happening, and this is already grounded. And the second one will be fixed. Once we apply a higher voltage into the first sphere, once we apply our high voltage to the first sphere, then what? Now we know that breakdown is not happening, and outside the control room we will start decreasing the distance. We will make the sphere come closer. So whenever this sphere is coming closer and closer, what will happen? Then the chances of having a breakdown is more. Right, so at a critical voltage value, at some critical distance, it will reach what? A critical voltage value, and that is why you will have a flashover and breakdown. Okay, that is why you will have a flashover and breakdown between these two spheres. That corresponding particular distance you will note down, and this d you will use in a chart. In a chart you will have the distance as well as what? The breakdown voltage, and you will use that. Like here you got a distance corresponding what is the voltage value. You already have a lookup table. That is what the voltage is under measurement. So this is the way you are going to use a sphere gap to measure high voltage. Okay. Let us see a bit more in detail. So I think I already explained you the working of the sphere gap. So let us just go through that again. What the first point? High voltage applied to one terminal and other stationary terminal is grounded. Then what? Distance is reduced and the breakdown of air between the sphere gap occurs and the gap distance is known. That is what we do. So we have a table like this. So we have already gap distance like 1 mm, 2 mm, 16 mm, 20 mm. You have a table like this for a particular diameter. For a particular diameter of the sphere gap, we have a table like this. For different diameter, your gap distance and breakdown also will change. So when we buy a sphere gap, with that you get a chart. Like what is the gap distance and what is the voltage. Voltage also what, like what? You have what? AC, DC as well as inverter. So once in my measurement, I got the 16 mm as the gap distance. So there in the table I will have what if I was applying an AC, then I will find this X value. If I was applying a DC, then it will correspond to Y, and inverse it will correspond to Z. Right? Because the breakdown mechanism will change with the type of the voltage that we apply also. So this way we will be able to find out. We will have a chart and we will be able to find out the high voltage quite accurately, not that much correctly, but quite accurately using sphere gap. And the procedure, once we find this, we don't stop there. As I told you, this we have already discussed the breakdown mechanism way back in material sciences SO. So it is not like once we conducted breakdown, you got a particular value. Next time when you are conducting, there is no need that you will get the same value. So the procedure will be repeated for 20 times, and the average gap distance is noted. Okay, we will not be using this particular value which we got for the first time. Instead, we will be doing the procedure for how much time? Many times, so 20 times normally, and find the average gap distance. Okay. So, and voltage level corresponding to the gap distance for AC, DC, and impulses formed on the chart. So, this is the procedure that we follow in order to find what, in order to use sphere gap to find the high voltage measurement. Now, let us see the conditions affecting breakdown of FF. Okay. Basically, there are 4 effects. There are more, but let us see the 4 major effects. One is what influence of the nearby Earth object. Second one is polarity of the applied voltage. Right. First one is what influence of the nearby Earth object. We will discuss one after another. Second one is polarity of applied voltage. Third one is temperature, pressure, and humidity. Definitely, atmospheric conditions when they vary, you will have a different breakdown voltage. Then what radiation of gap? That is again why you can say like another atmospheric condition, right? Like if you have radiation over the gap, that also will affect breakdown. We will see how. First of all, let us see the influence of the nearby Earth objects. Nearby Earth objects means what? Like you have a sphere gap like this. Okay, so this is your first one, this is your second sphere gap, and you are at a very high distance, so you are going to reduce it. Nearby you have another third object. Okay, some transformer bushing or something is there nearby. Okay, and this thing is already Earth also. This is Earth, and this here you are applying your high voltage, and you have a third object nearby, which is Earth. So what will happen when you compare the distances? The distance from here to here will be large, but distance to third one is what? It is lesser. Right? Distance to third one is lesser compared to distance to the other sphere gap. Right? So there is a chance. Like when I started decreasing this sphere gap distance. When I start decreasing the sphere gap distance, let me say after some time my sphere gap have reached till here, and then if at all this distance is this distance d1 is lesser than this distance d2. If d1 is less than d2, then what will happen? Maybe this distance will be enough for a flashover. That distance will be enough for a flashover to occur between what? To occur between 1 and 3. To occur for a flashover to occur between 1 and 3, this distance might be enough. Even though that time we are not having a breakdown between 1 and 2, which we will be using for measurement. So already some flashover happened. So some electron has lost through that way to ground. Then again we will reduce the distance and at a very smaller distance for a which does not correspond to the actual voltage. Like we apply a voltage and there is some distance d corresponding to it. But because of the third object in the vicinity, your distance in the final your d dash will be what? It will not be correspond to what? It will not be correspond to the original voltage. Or you will have, even though you are applying like 200 kV. Yeah, I apply 200 kV and this should be my measurement as per the distance. But what I will be getting? I will be getting like 180 kV measurement or 150 kV measurement. Understood? A smaller measurement, but it is not the real case. It is due to the earth object nearby your measurement. So that is the effect of the earth gap. So what we can do against that? It is quite simple. What we will do is that the sphere gap distance, the sphere gap distance is 2.5. Like you have a sphere gap, then what around that, whatever be the distance around that, your clearance will be what? If your clearance area will be 2.5. All your other equipment apart from this measurement thing will be outside 2.5 times the diameter of this sphere. So that is 2.5 times of the sphere. Yeah? So that is what we do for in terms of clearance. Okay. Another thing is that Like you have two sphere gaps and you have your third object, and first thing it was Earth, but now we have not earthing it and it is floating. In that condition, then what, your current can only flow to ground through this path only, and such objects which are not Earth are just kept nearby, which are not Earth. Such objects will not play any effect in what our breakdown of the area. So that is not an issue. But once it is less, that is a normal case when you go to a high voltage measurement laboratory. Every one of your equipment is Earth. Then you have to consider the sphere in this. So that is the effect of the sphere gap. Now let us see the effect of the polarity of the applied voltage. It is like this. Let us say first we are applying a positive polarity, or we are measuring a positive voltage. So these are my two sphere gap, and here you have positive polarity. This one is down, right? So what will happen? When you are having a high electric field around this, this is the anode and this is the cathode, right? So electrons can flow only from ground to this anode. So electron will flow like this, and because of that you have a spacebar formation, or I already told you like about the streamer propagation in the last semester. So because of that, let me say voltage V is applied here, and due to the streamer formation, your voltage a conducting path is established, and your voltage will become lesser. Right. So the space charge, this is called as space charge formation. This is called as space charge formation. That will happen at the anode when you are applying a positive polarity. So under that condition, already you got this voltage V, and already you got this voltage V at this distance, and you can have a breakdown. But this space charge formation will take quite higher time. The time required is quite higher, and that is why while moving this, while changing the distance, you will not move, and you will just reduce it. When you are reducing it, and you will just reduce it, and the breakdown will happen at a higher gap distance. So because of that, for a positive polarity, the measured voltage will be higher than the actual value. Mainly due to what? The time required for this process to happen is higher, and you are moving it faster. Okay, so because of that, you will have a high measured voltage than the actual value when it comes to positive polarity. And for the negative polarity, let us see. For negative polarity, what will happen? In a negative polarity case, again you have a sphere gap, and here you have the negative polarity. You are applying negative voltage, and this is ground. So what will happen? Electron will flow to ground like this, and there is no space charge formation here. It will just flow to ground. With that, it will form what a channel of electron flow will be created. That is why your breakdown, the time required, the process time is comparatively lesser, and that is why you will this breakdown will occur very faster. Like you are moving it, and the breakdown will occur very faster, and your measured voltage is lower than the actual value. So this is about the polarity of applied voltage. And similarly, you have other conditions like the atmospheric. So when I say when I have a chart, then it will be as per the atmospheric condition for what 180 or 760 mm of Sg and temperature of 25 degrees and humidity of 11 gram per centimeter cube. So these are the normal values as per the IEC standard. Okay. So we have the standard value, but that will not be the conditions under which we are making our measurement. So we should have some correction on that. Then there are different, like as the pressure increases, the breakdown voltage also will increase. Like you have a configuration like this, and first the pressure was lesser, then what number of molecules in the space is comparatively lesser. So breakdown chances will be what lesser. When pressure increases, first the breakdown voltage will increases because more density is there. That is why it will the breakdown voltage will occur at a higher rate. So this is there with pressure. Then when you have temperature, the temperature means what? Increase in temperature means you are causing the kinetic energy of the ions also will be higher, and that is why they will undergo collision faster. Right. So this distance, this process what? Like you are making your gap distance. So your gap distance will be what? It will be greater than the expected gap distance. Like for a standard condition, you are expecting your breakdown to happen at a particular distance. Now at a particular standard temperature. Now let me say your temperature is increased. Once your temperature increases, what will happen? Even this new d dash will be what? D dash will be greater than d, because your ions will have more kinetic energy and their collision will happen faster, which will lead to breakdown at a higher distance. So you will have a high breakdown voltage than the real case. So temperature is having this effect. Now humidity also. Similarly, humidity also is having its role. Like when you have a high humidity, then your gap distance will be more than the expected gap distance. So we find the relative air density using this formula. Like this, delta is equal to what? P into 270 plus 25. This is like standard thing, and divided by 70 into 270 plus 20. So using this formula, we usually find out the delta value or the relative air humidity. Now once we know the humidity value, again we have a chart for correction. Understood? So we know that humidity is affecting it, and we have a chart for correction. Like you have a delta, like it is not some kind of linear relationship. You have a delta value where it is 0.9, 0.9196 up to like this it is varying. Corresponding to each value, you have a correction factor. So that we use in our measurement. Like this, like once we have the V breakdown, whatever V breakdown, V normal breakdown we got, the V breakdown is given by what? K into V normal. So in order to find the real value, we will take the V breakdown measured divided by the K value. Okay. Similarly, this is the case here. Similarly, if humidity is also considered, then what we will get K raised to mv, where K is known as the correction factor. So the other K is for humidity value. So K is a correction factor, and m is the ratio between measured humidity to the standard humidity. Understood? So with this we can find out the V normal by using the correction factor of what? K raised to m, or K and the m, or the ratio between the humidity and the standard humidity. We can incorporate that in our whatever we measured, whatever be the normal value, we can find out this way. Okay. And experimentally, this is the value for E breakdown. The E breakdown is nothing but voltage in volt per meter. Right. That is how we normally explain the breakdown strength. That is given by 24.22 plus 6.08 by root D, where D is the distance between the distance or the gap distance between them. Okay. Apart from this, another effect which causes changes in the breakdown of air gap or changes in the measurement. Affect the measurement is the irradiation of the gap. Like you have your air gap like this, and there is some irradiation happening from outside due to light flashover, and maybe it is due to the flashover while measuring, flashover occurring while measuring. Anyhow, somehow if it is happening, the effect is that it causes the unwanted flashover affecting the voltage measurement. And what is the mechanism? Like UV light in the gap causes ionization, and thereby gets an early breakdown of the large distance. Just like temperature, your UV radiation of flashover, that light or the radiation also can cause what? That also can cause can impart more kinetic energy to the ions, and that will have more pollution, and that is why you will have a breakdown at a larger distance. So that these are the four things which affect the measurement things. So in the next class, we are going to see what the potential dividers, the second kind of measurement of voltage. So that you will see in the next class, potential dividers. Okay. So it is quite easier, the sphere gap, that we use the sphere gap for measurement of voltage, and you have seen what are the effects which are causes variation in the measurement. The four causes we have seen, and we also saw how we measure by incorporating what? K raised to m. It is the correction factor and the effect of humidity. So these things we incorporate also. In correction factor we incorporated what? The things with the pressure and temperature we incorporate. With m we are incorporating the humidity, effect of humidity. So this way we first saw one method for measurement of voltage. Next class we will see how we are going to use potential dividers in measurement of higher voltage. Thank you.